Hey everyone! So, today we're going to do something a little different. We're not actually going to write a single line of code. Instead, we're going to master the one skill that has to come before all of it: how to actually read a programming problem and figure out what it's really asking you to do. So, have you ever stared at a coding challenge and just thought, what do they really want? It's more than just a coding exercise, right? It's a logic puzzle and it's all wrapped up in words. These problems have their own language, full of goals, rules, and yeah, some hidden traps. Our mission today is to become expert translators, turning that dense text into a clear plan of attack. Here's what's on the menu. We're going to break down 3 classic problems: a permutation puzzle, a pathfinding challenge, and a partitioning task. And then we'll wrap it all up by building a sort of universal toolkit that you can use for pretty much any problem that comes your way. All right, first up, let's dive into the world of permutations. Just think of it like a shuffled deck of cards or a jumbled list of numbers. Our job is to try and bring a little order back, but, and this is key, with some very, very specific rules. Okay, so this is what you see when you open up a challenge. I know, it can look like a wall of text with all these instructions and formats and constraints. It can feel a little intimidating, but trust me, every single word on that page is a clue. Let's start picking it apart. The very first thing we have to do is nail down the core concept. And here, it's this idea of a fixed point. It sounds technical, but it's super simple. All it means is that the number in a specific position, or index, matches that position number. So if the number 3 is in the 3rd spot, bam, that's a fixed point. This is our target. This is what we're trying to get more of. Okay, now let's translate that wall of text into a simple to-do list. Step 1, we're given a jumbled list. Step 2, we're allowed to make one and only one swap between any 2 items in that list. And step 3, our goal is to maximize the number of fixed points we have after that single swap. Seems straightforward enough, but the real devil is in the details. And right here, this is the golden phrase. The catch, the crucial point, is exactly one swap. We're not trying to perfectly sort the list. That would be easy. No, we are looking for the absolute best possible outcome from a single strategic move. That one tiny constraint changes the entire game. And finally, we look at the constraints. Now, don't just glance over these numbers. The size of the list, n, can be up to 100,000. This is a massive clue. It's screaming at you that any solution where you just try every single possible swap is going to be way, way too slow. The constraints aren't just boring rules, they're signposts, and they're pointing you toward an efficient algorithm. All right, let's switch gears and move on to our second problem. This one's a classic. It's a journey puzzle. We've got a frog trying to get from point A to point B, and our job is to figure out the absolute cheapest way for it to make the trip. And again, here's the raw problem statement. We've got a little story about a frog, some positions, some costs. The main goal is pretty clear. Find the minimum total cost. But how is that cost actually calculated? That's where we have to put on our reading glasses and pay close attention. So at every stone, our little frog has 2 choices. It can take a short hop, just 1 position forward, or it can take a long leap, jumping 2 positions. Now, the long jump seems more efficient, right? Fewer jumps. But it comes with a penalty, this extra fee, F. And that immediately creates this fun little trade-off. Is it actually cheaper to take a bunch of small steps or a few more expensive leaps? So when we talk about total cost, it's not just one thing. It's the sum of the costs on every position the frog lands on, plus we have to keep track of how many of those big 2-position jumps it made and add that fee for each one. This right here defines the exact thing we're trying to make as small as possible. And here it is, folks, 2 little words that change everything, in addition to. This is the catch. It would be so easy to misread this and think that the fee replaces the landing cost, but the problem makes it crystal clear. You pay both. If you miss those 2 words, you are guaranteed to get the wrong answer. Okay, for our final example, we're going to look at a partitioning problem. This is all about taking one big thing, in this case, an array of numbers, and breaking it down into a specific number of smaller continuous chunks, or blocks. And of course, we have to do it in the most cost-effective way possible. So here's the problem statement. A few key phrases should just jump right off the page at you. Partition it, contiguous blocks, and, you guessed it, minimum total cost. We're basically dividing and conquering, but the rules for how we calculate the cost of each piece are, well, they're pretty unique. And just like before, there's a killer keyword here, exactly K. Not at most K, not at least K, exactly that number. This precision is a really powerful constraint. And that other word, contiguous, means the blocks have to be made of elements that are next to each other. You can't just cherry-pick numbers from all over the array. Now, this is where things get really interesting, maybe even a little weird. The core logic for calculating the cost is totally unique. It all depends on whether a block has an odd or an even number of elements in it. For odd-length blocks, the cost is based on the maximum value in that block. For even-length blocks, it's based on the minimum. This strange-sounding rule is the absolute heart of this entire puzzle. Let's check those constraints again. The array size n is only up to 500. Remember our first problem? It was 100,000. This is tiny in comparison. And that is another huge clue. It suggests that a solution that might be considered slow or inefficient for the first problem could be totally fine here. The constraints are practically telling you what kind of algorithm you should be thinking about. So, after tearing apart 3 pretty different problems, what have we actually learned? What's the big takeaway? Well, we can distill this whole process down into a simple, reusable toolkit for reading pretty much any challenge. It really boils down to a simple, repeatable checklist. First, isolate the goal. Are we trying to maximize something or minimize it? Second, identify all the actions you're allowed to take. Swapping, jumping, partitioning, whatever it is. Third, hunt for the catch. Those critical little keywords like exactly one or in addition. Fourth, scrutinize every constraint. They are giving you massive clues about efficiency. And finally, translate the plain English sentences into concrete logical rules, just like we did with those weird odd and even block costs. You see, at the end of the day, learning to read a problem like this is about so much more than just coding. It's a system for structured thinking. It's about taking any complex, messy goal, whether it's planning a trip on a tight budget or organizing a huge project at work, and breaking it down into a clear goal, a set of defined actions, and a list of known constraints. So, what will you use it for?